Good evening, everyone. We are in the week 11 problem solving session of the NPTEL course Control Engineering, and week 11 is about state space analysis. I am Teja Golla, a fifth year research scholar working under Professor Santanu Kapat at Embedded Power Management Lab, IIT Kharagpur. Let me share my screen. So I hope you can see my screen. So in this lecture, we are going to discuss about state space analysis. So first we'll see why state space is needed, why state space modeling is needed, when we have already learned how to design controller everything using transfer function based approach as well as root locus based approach. So why is it needed in the first place? So to start with, first let us see what are the advantages and drawbacks of the transfer function based design. So let me quickly summarize it. So transfer function based design. First of all, it is very easy. So one thing is it is very dominant approach and widely used. Also widely used in the industry. Okay. And also it is easy because any differential equation will be converted into an algebraic expression and it is easy to solve. So it is basically also having an algebraic property of transfer functions. Okay, and it is also very easy. Also, it is widely used in the industry, and it is also easy, as we can see. We have seen in the earlier weeks how we are able to design the controller based on the transfer function, the frequency domain approach. Also, in different domain, we have done based on the time domain, where we have designed using the peak overshoot, etc. And also, we have designed using the root locus approach. So there are also limitations to this transfer function based approach because the very first limitation it is only applicable to linear systems, applicable to only linear systems, because if a system is non-linear then we do not get the transfer function, because transfer function is only based on an LTS system, linear time invariant system. So what happens if the system is non-linear? Then you can't go by transfer function approach, and that is one limitation. So other limitations are it is limited to single input, single output system. Limited to single input, single output system. So if a system is having multiple inputs or multiple outputs, then you can't basically define a transfer function, give a particular transfer function. Although you can have a multiple transfer functions from each of the input to each of the output. So there are so many permutations and combinations. And even in that scenario, the number of transfer functions will be more, and it will be very easy, very difficult, sorry, very complicated, as well as difficult to understand what is happening and how to design a controller. So in that uh, cases where the system is either nonlinear or it is multi-input, multi-output system, the transfer function based design may not be applicable, and we may not get the benefit of transfer function based design, and we might have to go to a different approach or a different approach based controller design, and which is the state space based approach. And today we are going to discuss about the state space. So today we'll start with the state space modeling. First I'll discuss about the generic form. So state space model. So we can say we have a system. So it is of nth order, means there are n states. Nth order, that implies it has n states. So in that case, we can define it as x dot is equals to ax plus bu and y is equals to cx plus du. So this is how we are representing the input as well as output with the states of the system. So now if we expand this, because we have n states, what is x corresponding to what is u corresponding to what is b corresponding to. So here u can be single input as well as multi input. So it is a generic. So x is of n states and a is a matrix, b is a matrix, c is a matrix, d is a matrix. Y is output. Again, it can be multi output, single output, and u is an input. Again, it can be multi input or single input. So now if we expand it, we'll get x1 dot x2 dot up to so on xn dot is equals to A matrix will be an n cross n matrix. So I can write it as something like A11, A12 up to so on A1n, then A21, A22 up to so on A2n. Now if we come to the last row, it will be AN1, AN2 up to so on ANN. Okay, so this is the A matrix that we'll obtain. Into again X we have. So it is state vector x1, x2 up to so on xn. Okay. Plus again now we have a B matrix. Say if it is single input, we'll have one column in B. If the inputs are M, then we'll have M such columns. So currently I'm considering a single input. So it will have one column B1, B2, B3 up to so on Bn into single input I'm considering. So U. So this is the details of the first equation. Now if we go to the second equation, again I'm considering single output, but it can be multi output also, but for the time being I'm considering single output. So y is equals to, because it is single output, now C matrix will be a row vector, and then it will be C1 C2 up to so on Cn multiplied by the state vector x1 x2 up to so on xn plus d is just a scalar because u is also single input. So d can be written as scalar d, or I'll use a different color d. Sorry. If I use a different color, d into u. So this is how we define a generic state space model. So I'm considering a system with n number of states. So it will be an nth order system. And for any order of the system, we can define it as x dot is equals to ax plus bu and y is equals to cx plus du. And here are my matrices, the order of this matrix. So if I have to define this, let me use a different color. So this will be my A matrix, which is basically n cross n. And this is my B matrix, which is basically n cross 1. And this is my C matrix, which is basically 1 cross n. And then this is my D matrix, which is basically 1 cross 1. So in this way, I'll get the matrices and then I can obtain the relation between the inputs as well as outputs, as well as what are the states in a given system. And now based on this, we can design a controller. The controller design will not be covered in this week, but it will be covered in the next week. So in this week, we are going to understand this state space modeling, different type of representation, how to get a model from a transfer function, how to get the transfer function from a given model. So all these kinds of basic fundamental concepts that are needed to design using the state space modeling, we'll be learning all those things in today's session. So this is all about the state space model. So similarly, for any given system, we can consider the state. Say series RLC circuit is there. We can consider inductor current to be one state and capacitor voltage to be another state, and we can get the state space model of series RLC, or say higher order RLC network. In the same way, we can get for that circuit as also, and for spring mass damper system also we can get. And these are all the examples that sir has already covered in his lecture, so I'm not taking up those examples in today's session. So just to start with, say if we have such differential equation, how are we going to get the model? So I'm not going to teach for an nth order, because whatever I'll be teaching for third order, it will be equally extendable for an nth order system also. So I'm not teaching for nth order as such, but I'll be showing for one such example where I have considered a third order system. So the question is as follows: consider the following third order linear differential equation, obtain the state space equations, and determine the matrices A, B, C as well as D. So the equation is 2 into d cube y by dt cube plus d square y by dt square plus 6 into dy by dt plus 10y is equals to 10 into u of t. So now I'll just rewrite it in a different way so that it will be easy to understand. So I'm rewriting this equation as 2 into y triple dot plus y double dot plus 6 into y dot plus 10 into y is equals to 10 into u of t. So whenever we see any such linear differential equation, so first we have to assume what are the states, and then after getting the states, then we have to write the individual equations. So if the system is of nth order, you will get n such equations. But if it is second order, you will get two such equations. So here we can see it is of third order. So we'll get three such equations. So we need to choose three states. So this is a third order system. Third order system, which means three states are to be chosen. So every time we'll choose in this way. So the first state x1, I'm choosing it to be y. And then the other states will be derivative of those. So x1 is y, x2 is x1 dot, which is equals to y dot. So this is y, this is y dot. And now x3 is x2 dot, which is x1 double dot, or I could say y double dot. So I'm choosing my states in such a way that they are the derivatives of a variable y. Here y is a variable, y need not be output, or maybe it is an output also. So y is a variable, and I'm choosing the states of this system as the derivative of the this y variable. And how do I know that I have to stop at 3? Because I know that the system is third order, so I have to consider three states. So I have considered y, y dot, and y double dot. And if I go back to the state space modeling, I can see that this matrix, or I would say each line, LHS is x1 dot and RHS is consisting of x1 as well as u. So now I have to calculate x1 dot, x2 dot, x3 dot, and based on that, I'll be getting my relation between the state vector derivatives as well as state vector as well as the input. So from this, we can write it as, so first equation is x1 dot. So I know x1 dot is nothing but x2. And the second equation is x2 dot, which is nothing but x3. But how do I get x3 dot? X3 dot is what? X3 dot is nothing but y triple dot, which I can get from the given equation. So if I take everything onto the right hand side and divide by 2, I'll get y triple dot expression, which is minus 5 into, sorry, let me change the color. So I'll go back to black color. So it is minus 5 into black color, minus 5 into y means x1. So minus 5x1, then minus 3 into y dot, which is x2, then minus 1 by 2 means minus 0.5 into how much? Y double dot. So it is basically x3. So I'm writing everything in terms of the states x1, x2, x3. And then we also have u of t in this, which is plus 5 into u of t. So these are the three equations that I'll be getting for the given differential equation. Now what we'll be doing now, we have to choose or write the equations. So I'll write it in terms of matrix. So I have x1 dot, x2 dot, x3 dot. So on the left hand side, I have this matrix. Or maybe I can, because there is so much space, let me write it with more gap. x1 dot, x2 dot, x3 dot. Okay. So now we have another matrix, which is 3 cross 3 because this is a 3 cross 3. Now here we have x1, x2, x3. And then we have B matrix. And then here we have U input. Okay. So now I have to fill this 3 cross 3 matrix from the equations that I have obtained. So x1 dot is x2, x2 dot is x3. So x1 dot is x2. So if it is x2, then what will be the three elements in the first row? As if we are multiplying the matrix uh, A with the x state vector, we should get x1 dot. So x1 dot is nothing but x2. So the first row will have only 0, 1, 0, 1, 0 because it is x2 and there is no input also. So it is 0. And then x2 dot is nothing but x3. So we'll have 0, 0, 1 and then input is 0. The third matrix is minus 5x1. Then we'll have minus 3x2. Then we'll have minus 0.5 x3. And then here it is 5 into u. So in this way, we are going to get the uh, the first equation. Then if my output is say considered to be y, say if I am considering my output to be y, then it will be C matrix into x. So this is C matrix will have three terms into x1, x2, x3. x1, x2, x3. Say my y is the output. I know y is nothing but x1. So it should have only x1. So the vector will be 1, 0, 0. And there will be no d because there is no relation between the input as and output. So the d is not there and we'll have only C matrix. Basically d is nothing but 0. So I can write it as plus 0 into u. Okay. So I'll just quickly discuss what I have explained or taught till now. So this week the lecture is about state space analysis. So first we have understood why transfer function based design is limited, like or what are the drawbacks. So although it is very dominant approach as well as it is widely used in the industry and also it is easy to understand because of the algebraic property of the transfer function because if we are multiplying in time domain, it is basically addition in the transfer function and you can add the transfer functions, multiply by the transfer functions if they are cascaded, if they are connected in parallel, you add them. So all these things are there. But however, the limitation of the transfer function is that it is only applicable to linear systems. You cannot apply to non-linear systems. And also it is limited to single input, single output system. And if you have multi-input, multi-output system, you will have permutations and combinations of transfer functions. And it will be very complicated as well as difficult to analyze in transfer function based domain. So now we in these two lectures, first week 11, we'll be learning about the state space analysis and then in the next upcoming week we'll learn the design using the state space. So in this week we'll be learning about the state space analysis. So I have started with a system which is of nth order which has n states. So x dot equal to ax plus bu and y is equals to cx plus du. And if we consider n states, then the a b c d matrices can be written as shown over here, where a is n cross n matrix, b is n cross 1 matrix, c is 1 cross n matrix, and d is a scalar which is 1 cross 1 matrix. So I have considered one problem where I have considered a third order linear differential equation, and the question is to obtain the state space equation and determine the matrices A, B, C, and D. So the given equation is 2 into d cube y by dt cube plus d square y by dt square plus 6 into dy by dt plus 10y is equals to 10 into u of t. So now I have rewritten the given equation in such a way that it is in terms of y and y derivatives. So it is 2 into y triple derivative plus y double dot plus 6 into y dot plus 10y equal to 10 into u of t. So I know that the system is third order. So I have to choose three states. So whenever there is linear differential equation in this way, always start with the y and then consider the derivative of the y as the states. So the system is of third order, so I have to consider three states. So starting with y, I have to get two more states. So I'll consider y dot as well as y double dot. So y I have considered as my state x1, y dot I have considered it as x2, y double dot I have considered it as x3. So from this I can calculate x1 dot, x2 dot, and for x3 dot I'll be using the given equation, and then I'll be getting the three equations. Now these three equations I have written in matrix form. So from this matrix now I'll be getting the A, B, C as well as D matrix. So in this way, for a given differential equation, we can get the ABCD matrix and we can represent it in the state space form. So if this is clear, then I'll move to the next topic, which is state space to transfer function. So I have given a state space. Can I calculate the transfer function? Because say the state space is single input, single output as well as linear. So given that it satisfies all the conditions under which we can get the transfer function, can there be any correlation between state space to transfer function? Yes, there is state space to transfer function correlation, and this is unique. So one important thing is state space to transfer function is unique. However, maybe I'll use a different color. However, the other way around is not true. This is unique. However, transfer function to state space is not unique. So it can have multiple solutions. And we'll also see few of them today. Transfer function to state space is non-unique. So currently we are discussing about the first one, state space to transfer function. And then we'll see whether we are getting the transfer function or not. So we know that the state space model is represented as x dot is equals to ax plus bu, y is equals to cx plus du. So what we'll do is first we'll apply the Laplace transform on the first equation. So if we apply Laplace transform, so apply Laplace transform. Then we'll get s into x of s into x of s is equals to a into x of s plus b into u of s. So now if I bring x of s everything in this side, I'll get si minus a into x of s is equals to b into u of s. So if I take inverse, then I'll get x of s is nothing but si minus a inverse into b into u of s. So now this is my first equation, solution to the equation 1. So if I call this as equation 1 and then apply the s or the Laplace transform to the second equation. So do the same, apply Laplace transform. Okay, then we'll get y of s is equals to c into x of s plus d into u of s. So this is what I'm calling it as equation 2, or I'll use the same color. Say this is equation 2. Now substitute equation 1 in 2. So substitute because x of s is calculated. So substitute. So once we do that, what are we going to get? We will be getting y of s is c into x of s is what? Sa minus a inverse into b into u of s. Plus again we have d into u of s. So now take u of s common. So y of s is nothing but u of s into C SA minus A inverse B plus D. Okay. So now if I bring back everything like U of S to the LHS side, then I have input output relation. So now my G of S, which is defined as Y of S by, sorry, which is defined as Y of S by U of S is, or can be written as C into SA minus A inverse B plus D. So this is how we'll get a transfer function for a given model. So if we are given the state space model, which is in terms of ABCD matrices, and then if we are asked to calculate the transfer function, then this is how we can calculate. So no need to derive it every time. This is a standard formula that we can remember, and it will be uh, helpful in many topics. So G of S is nothing but C into SA minus A inverse into B plus D. So in this way we can calculate the transfer function. So for a given system, if it is multi-input multi-output, then it is not recommended to go by transfer function based approach, and we should go by state space approach. However, if it is single input single output, we can convert the given state space model into transfer function, and then we can still get the transfer function from there, and then we can calculate whatever we are going to design, or whatever poles or stability that we are going to check, we can check from the transfer function. But we are also learning how to correlate between these two. Say one is given, how to calculate the other one. If the other one is given, how to calculate this one. So here we have started with the first one, which is state space to transfer function, which is unique. Then eventually later in today's session, we'll be discussing how to convert the transfer function back to state space, which is again non-unique. So let us solve one problem based on the first thing, which is state space to transfer function. ABCD matrices are given as shown over here. First, we are asked to calculate the transfer function. Once we calculate the transfer function, we have to comment on the stability of the system. How are we going to comment on the stability? By calculating the poles, whether they are lying on the LHS, LHP, left half plane, or on the imaginary axis, or on the RHP. Based on that, we'll comment on the stability. For that, we need to have the transfer function. So let us use the equation that we have obtained just now to calculate the transfer function. So it is C into SA minus A inverse into B plus D. So since D is 0, we have to calculate C into Si minus A inverse into B. So C and B are given. Si minus A is something we have to calculate, and then we have to apply inverse to that. So first let us calculate Si minus A inverse. For that, let us calculate Si minus A. So Si is what? S0, 0, S minus A, which is 0, 1, minus 2, minus 3. So now we'll get S minus 1, 2, S plus 3. So this is my Si minus A. Now for this, I have to calculate the inverse. So first let us calculate determinant of Si minus A. So mod of Si minus A is S into S plus 3 minus of 2 into minus 1, it is minus 2. So it is S square plus 3S plus 2. Now I can calculate Si minus A inverse as adjoint of Si minus A by Si minus A determinant. So the determinant is obtained as 1 by S square plus 3S plus 2, and then adjoint is nothing but S plus 3 S, and this will be 1 and minus 2. Okay, so if I multiply this, I will get the SA minus A inverse. But for the transfer function, I have to calculate C into SA minus A inverse into B. So my G of S, let me use a different color. My G of S is C into SA minus A inverse into B, and D is 0. So I'll not cancel anything. I'll keep the determinant as it is, and I'll perform the matrix multiplication so that I'll get the final transfer function. So I'll take the determinant outside, which is 1 by S square plus 3S plus 2, S square plus 3S plus 2. Then C is nothing but, what is C? C is 1 0 and B is 0 1. So C is 1 0 into SA minus A inverse. So it is S plus 3 1 minus 2 S, and B is 0 1. So first I'll perform this matrix multiplication. So if I perform this, I'll get 1 as well as S. So this is this. If I multiply by 1 and 0, then I'll get basically 1. So overall, these three matrices multiplied will result in the numerator as 1. So now my transfer function g of s is nothing but g of s is equals to 1 by s square plus 3s plus 2. So this is how we'll be getting g of s, which is g of s is equals to 1 by s square plus 3s plus 2. So this is the first part where we were asked to calculate the transfer function. Now, how can we comment on the stability? By calculating the pole locations. So let us quickly check this. The second part, I have to consider the denominator and then equate it to 0 and then check the pole location. So it is s plus 2 into s plus 1, which means s is equals to minus 1 comma minus 2. This means the system is stable because both are on the left hand side. So in this way, we can calculate the transfer function for a given state space model. Any doubts until this point? Okay. So if no, then I'll just show a MATLAB code that is there. So this is state space to transfer function. So first we are clearing the command window as well as workspace and then closing all the plots. Then how to calculate the state space to transfer function. So first we have to write the A matrix, B matrix, C matrix as well as D matrix. So my A matrix is 0 1 minus 2 minus 3. So 0 1 and next row means semicolon minus 2 and minus 3. Within the row you have to give spacing. Within the column you have to put semicolon, and then B is a column matrix, so 0 semicolon 1, and then C is row matrix, so 1 space 0, and then D is basically 0. So there is this transfer function, there is this command where you can write state space A B C D. So this will give result in system. Now we are calculating the transfer function of system, which is stored in G, and then I'm displaying G. So let us see if I think I can run from the top itself. So if I run this. So my g is 1 by s square plus 3s plus 2. So if I do ZPK of g, then basically I'll get 0 pole locations as well as gain. Sorry. So it is 1 by s plus 2 into s plus 1. So the pole locations are minus 1 as well as minus 2. And so the system is stable because all the poles and there are no zeros are on the left hand plane, left half plane. So in this way, we can calculate the stability of the system. Any doubts until this point? Okay. So if no, then I'll move to the next topic, which is linearization. Till now, we have considered the state space model to be linear or a linear combination of x1, x2, x3, x4 states. But what happens if the system is not linear? What do I mean? Say I have x1 dot. Previously, it was some scalar product of the states and addition of that. But what if it's a function? Say f1, x1, x2, x3 up to so on xn comma u because it's a function of u. Similarly, x2 dot is equals to f2 x1 x2 x3 up to so on xn comma u. Similarly, we have xn dot which is fn x1 x2 x3 up to so on xn comma u. So these functions are non-linear. So these functions are non-linear. So in that case, how do I get the state space model? So uh, first thing, all the systems in the our day-to-day life are all non-linear. So how are we going to design the controller? So we use some concept called linearization, where we'll be linearizing the given nonlinear system around an operating point, and then we'll try to design the controller around that operating point, and also comment on the stability around that operating point. So now the question is, what if there are multiple operating points? Then we have to analyze the system around each of those operating point, and then linearize them around those operating points, check the stability around those operating points, and design the controller for each of those operating points. So in this way, if we have more operating points, we'll have to design the controller for each of them, and this is called gain scheduling method, which is also what sir has mentioned. So they will have different gains for different operating points based on the state variables. So if the state variables are close to one operating point, they'll have one set of gains. If they're moving towards another operating point, they'll have different set of gains. So first of all, what is the equilibrium point or operating point? So equilibrium point means equilibrium point. So if the system starts at the equilibrium point, it stays there. So for this to happen, the condition is x1 dot is equals to 0, x2 dot is equals to 0, up to so on, xn dot is equals to 0. So if all the derivatives of the states, which means there is no change in the state, so it is fixed. So this is called an equilibrium point. So the solution to all these equations will result in an equilibrium point. So solution to this equation. And now we are trying to linearize it, and then we'll get an A matrix as well as B matrix. So let us see how we are going to get the A matrix. So first I'm writing the A matrix. So we will be performing partial derivative of each of these functions with each of these variables, and then we'll try to calculate that value at each of the operating points to get the A matrix, similarly B matrix, similarly C matrix, as well as D matrix. But currently I'll show A and B matrix, then I'll show the C matrix. So the elements of the matrix will be, in the first row, it will be partial derivative of F1 with respect to all the states, dou F1 by dou X1, dou F1 by dou X2, up to so on, dou F1 by dou Xn. And in the second, we'll have partial derivative of F2 with all the states, dou F2 by dou X1, dou F2 by dou X2, up to so on, dou F2 by dou Xn. Then if we come down till the last, it is dou Fn by dou X1, dou Fn by dou X2, up to so on, dou Fn by dou Xn. So this is the overall matrix of A. So basically, if I have to write in terms of the state space model only, then I think it would make more sense. So we have x1 dot here, x2 dot here, up to so on, xn dot here. So this is equals to this into x1, x2, up to so on, xn. Plus similarly B matrix, now we will be differentiating with respect to U. Say if it is single input, again we'll have one column. If it is multi input, then we'll have multiple columns. So now it will be dou F1 by dou U, dou F2 by dou U, up to so on, dou Fn by dou U into U. So in this way, we are going to get the linearized model for a given nonlinear model. So now I have to do this for each of the operating point, because these expression are fixed because the given system is fixed. Now at what equilibrium point I'm calculating this, that will decide. So I have to perform this for each of the equilibrium point. So now what I will do is I'll calculate the matrices for each of the equilibrium points. And then we'll get different ABCD matrices for each of the equilibrium points. And then for that equilibrium point, check the stability. So check the stability at each equilibrium point. Check the stability at each equilibrium point. So now the very first question is, can a system be stable for one equilibrium point and unstable for the other equilibrium point? Definitely yes. There are so many systems where system is stable at one equilibrium point and unstable at another equilibrium point. So the famous example is the uh, inverted pendulum. So if I consider, say, this as a pendulum, this position is a stable equilibrium point, because if I give any perturbation, it will come back and settle here. Whereas this is inverted position, and if I give any perturbation, then it will come to the other equilibrium point, which is stable. So the top point, this point is unstable equilibrium point, because any perturbation will make sure that it will never go back to that initial point. So this top point is the unstable equilibrium point, and this is the stable equilibrium point. So in this case, what we have to do is, say we have inverted pendulum, which is a nonlinear system, because it is a function of sine theta. Now we'll linearize the model at this operating point. Also, we'll linearize the model at this operating point. And then once we get one linearized model at this inverted position and one linearized model at this normal position, we can check that the system is unstable at the top and stable at the bottom, which is also what we are getting. So this is the unstable equilibrium point. Any perturbation will make sure it will come down, and this is the stable equilibrium point. So any perturbation will make sure that it is still here. So in this way, this is one famous example that people know, but in such way, there are enormous problems where you can get multiple equilibrium points, and the dynamics can be very different for each of these equilibrium points. And with deeper, if we go deeper into the nonlinear dynamics, there are many things like limit cycle, which sir has considered, I think, for the predator prey model. Also, he has considered one van der Pol oscillator, where it will go in a loop. So it will not come out of the loop, but it is within the loop. Like, say, sir has considered one predator prey model. So where there are tigers, where there are deers. So for a certain initial condition, it will go on a loop, which means the population of the deers will increase and decrease. Similarly, the population of the tigers will increase and decrease, and this will go in a loop. So there is no equilibrium point, but it will increase and decrease, increase and decrease, and it will keep on going in the same loop. So that's how, and these limit cycles are there. And sir has discussed that, but due to time constraints, I may not be able to consider any problem and show. But I have showed one predator prey model in the beginning weeks, I think first week, if I'm not wrong. So you can go to that video and check there. But since there are many other topics that has to be discussed in today's session, I'll not be covering that limit cycle oscillation example. But however, I'll discuss one problem, and I'll show how to calculate the equilibrium points, how to compute the Jacobian matrix, and then how to calculate the linearized model at each of these equilibrium point, and also determine the stability of each equilibrium point. So when we say stability, it's around that equilibrium point, because if it starts at equilibrium point, it will stay even if it's an inverted pendulum. So say, even if it's an inverted pendulum, if it is exactly at the inverted position, it will stay there. It will not move from any of there. But say if I have started slightly from the other side, then it will come down. So any initial condition starting at the equilibrium point will stay at the equilibrium point, and that is what our definition is also saying, that change in the state variable is zero, which means the state variable will be same with the time if it starts at the equilibrium point. However, if it is stable equilibrium point, even if it's a small perturbation, it will come back to the equilibrium point. Whereas if it's unstable equilibrium point, any perturbation will make sure that it is moving away from the equilibrium point. Yeah. So let us consider this example. So as I have discussed, this will be my f1, which is a function of x1, x2, as well as u. And this is a function of f2, which is x1, x2, as well as u. So in this case, there is no input. So input is zero. So my B matrix is zero. But say if there is an input, then I'll get a B matrix as well. So first point is calculate the equilibrium points. So I have told that equilibrium points means state will not change. So x1 dot equals to 0 as well as x2 dot equals to 0. So for these equations, I have to calculate the values of x1 and x2, and maybe there can be more than one equilibrium point, we'll never know, so we have to check. So x1 dot equals to 0 means x2 is 0, so x2 is 0 is one of the solution, and then other one is minus x1 plus x1 cube minus x2 is 0, so this is equals to 0. So if I take x1 common, I'll have x1 into x1 square minus 1 equals to 0. So the solutions are x1 equals to 0 plus 1 and minus 1. So x2 equals to 0, but x1 has three such points, which means there are three equilibrium points. So the equilibrium points are basically three. So equilibrium points are three. So we have three such equilibrium points. So if I write x1 and x2 as the state vector, what are those equilibrium points? So the first one is simple, 0 0. Second one is 1 0. Third one is minus 1 0. So these are the three equilibrium points. Now, as I have said, you have to now calculate the linearized model at each of these equilibrium points, because the dynamics will vary depending upon the equilibrium point, because the Jacobian matrix, one thing I forgot to mention, this is the Jacobian matrix. This is the Jacobian matrix. So this Jacobian matrix value will differ when you are calculating at one equilibrium point. As you move towards another equilibrium point, it will change. So the stability of the system can change. So you have to calculate this Jacobian matrix for each of the equilibrium points. So first, let us compute the Jacobian matrix in terms of x1 and x2. Then later we can calculate the Jacobian matrix at each of these equilibrium points. So the second part, also there are less than a min, okay, nothing. So the second point is Jacobian. So I'm calculating the Jacobian J. So since it's a second order system, we'll have 2 cross 2. And as we have discussed, the expression will be dou f1 by dou x1, dou f1 by dou x2, dou f2 by dou x1, and then dou f2 by dou x2. So now I have to partially differentiate f1 with respect to x1. Since there is no x1 term, I know that it is going to be 0. And then if I differentiate f1 with respect to x2, I'll get 1. So it is 1. And if I differentiate f2 with respect to x1, I'll get minus 1 plus 3x1 square. And then if I differentiate with respect to x2, I'll get minus 1. So this is what I'm telling about. If you see, this matrix A, or whatever Jacobian matrix, is a function of x1. So the value of J will vary when we are calculating at different operating point. So with this, we can see that the stability of the system may alter depending upon the different value of equilibrium point, which will again alter the Jacobian matrix. So if you see, we have computed the Jacobian matrix. Now we are trying to linearize the system about each equilibrium point. So since U is not there, my B matrix will be 0. So this is my A matrix. So this is my A matrix. B matrix is 0, simple. And then say y is x1. Say if y is my x1, then y is equals to c into x, right? So y is x1, then y is equals to c into x, which is x1, x2. So there is not much difficulty in y. So the main issue is coming for the x dot equal to ax plus bu. So we have to calculate the x matrix for each of this. So x dot equal to ax plus bu. So calculate a for each of the equilibrium points. For each of the equilibrium points. So we are going to do this and then see how we are going to get the different matrix. So first I'll start with the equilibrium point 0 0. So the third point is linearize the system about each equilibrium point, and then let us see. So the third point, first I am calculating the A matrix for 0 0 transpose. So if both are 0, then my A matrix will be 0, 1, minus 1, minus 1. 0, 1, minus 1, minus 1. Okay, so if this is my A matrix, and then if I write the x1 dot x2 dot, I'll get something like this. X1 dot x2 dot is equals to my A matrix, which is 0, 1, minus 1, 1 into x1, x2. Since u is 0, we'll get this type of A matrix. So for equilibrium point 0, 0, we are getting A matrix as 0, 1, minus 1, 1. Now let us calculate for the other equilibrium point 1 and 0. So 1, 0 transpose. If my other equilibrium point is 1, 0 transpose, then what A matrix am I going to get? So A matrix is, so three terms remains the same. So x1 is 1, so this will be 3, 3 minus 1 is 2. So 0, 1, 2 minus 1, 0, 1, 2 minus 1, 0, 1, 2 minus 1. Okay, so now if I rewrite the x state vector in terms of A matrix, then I'll get x1 dot x2 dot, which is equals to 0, 1, 2 minus 1. And we have x1, x2. So now we can see the A matrix is different for these two equilibrium points because it is dependent on x1 and x2. Whereas in the earlier cases, whatever we have seen, A matrix is constant because it is linear, and it is not, A matrix is not a nonlinear function of x1 and x2. So it is a scalar multiplied, a fixed constant, I should say, constant multiplied by state vector. So A matrix is constant and it is not function of time, or it is not varying with any of the state variables nor with time. Whereas in this case, if we see, the function is a nonlinear function of x1 and x2. So even if we do partial derivation and even if we try to linearize it, that A matrix, or in some of the terms of the A matrix, are a function of the states x1 and x2. So the A matrix itself will change. And we know that the eigenvalues of the A matrix will define the stability of the system. So the stability of the system is dependent on the states. So at what point we are operating also decides the stability of the system. So if we are close to one operating point or one equilibrium point, it will have one type of stability. If we are moving away, it may have a different set of stability criteria because it's a function of x1. So the location at which we are starting with, or the initial condition, will very much guide the uh, trajectory, or I would say how x1 and x2 are varying, because the initial condition will decide around which operating point we have started, and then depending upon at which operating point we are, that will decide the stability. So that will guide whether x1 and x2 will deviate away or move away from the operating point, or move closer to the operating point. Now, if I do the same for the third one, which is minus 1, if I'm considering x1 to be minus 1, since it is x1 square, it will be same as the third case. So my equilibrium point is minus 1, 0. So the A matrix is same. So for two cases, we are getting the same matrix. A matrix means the stability criteria for these two will be the same. So A is nothing but 0, 1, 2, minus 1, because it is x1 square. So whether it is plus 1 or minus 1, it is going to be the same. Now we have x1 dot and x2 dot. And then we have 0, 1, 2, minus 1. Then we have x1 and x2. Okay. So now we have calculated the third part where they have asked to calculate the uh, each linearized state space model at each of this equilibrium point. So we have obtained the equilibrium point. At the beginning we have obtained the equilibrium point, and we have seen there are three such equilibrium points. But it may be so that there is only one equilibrium point, right? So in this question there are three, but it may not be always more than one. It can be one, it can be two, it can be three. But depending upon the order of the system, it will be decided. If the order is third order, at max it can have three solutions. If the order is three, it cannot have four solutions. So the maximum number of equilibrium points is again the order of the system. So the number of equilibrium points is always lesser than the order of the system. Once we got the equilibrium points, we have calculated the Jacobian matrix, generic matrix in terms of x1 and x2. And we have seen how the A matrix is dependent on x1 as well as x2. And then we have seen that for each of the operating point, the A matrix value may vary. And then we have also seen how the A matrix is varying for different equilibrium points. And we have seen out of these three, two have the same A matrix because x1 and x1 square are same for x1 equal to 1 as well as minus 1. So two of them will have the same stability criteria and the other one will have a different stability criteria. So before we go into stability criteria, if you have any questions, you can ask. The meeting might end soon. Once it ends, we'll join back and check the stability of each equilibrium point. And then we'll move to the other subsequent topics. So once this meeting ends, kindly join back. Uh, in the meantime, if you have any questions, you can ask. So now that we have calculated the A matrix, let us calculate the eigenvalue of each of these A matrix and comment on the stability. So the fourth part is the stability. So fourth part is about stability. Uh, in this part, first let us start in the same sequence 0, 0. So my x1 and x2 subpart is 0, 0 transpose. Okay, so now in this case, I will be considering my A matrix, whatever I have obtained here, which is 0, 1, minus 1 and 1. 0, 1, minus 1 and 1. So my A matrix is 0, 1, minus 1 and 1. Okay, so how to calculate the eigenvalues? Determinant of lambda, that of lambda I minus A. So I'll get lambda minus 1, 1, lambda minus 1. So I have to calculate the determinant of this and equate it to 0 to calculate lambda. So lambda square minus lambda plus 1 is equals to 0. So if I calculate lambda, I'll get lambda is equals to minus b 1 plus or minus square root of b square minus 4ac. So I'll get minus 3 by 2. So clearly you can see that it is 0.5 plus or minus j root 3 by 2. So there is one RHP pole because eigenvalues corresponds to poles. So we can see that there is clearly one pole or one eigenvalue which is on the RHP side. So it is unstable. So what we have done, we have considered the A matrix and then we try to calculate the eigenvalues to comment on the stability. So determinant of lambda minus A is lambda minus 1, 1 and lambda minus 1. And then we have calculated lambda square minus lambda plus 1 equals to 0. So b square minus 4ac minus b plus or minus square root of b square minus 4ac by 2a gives me one eigenvalue on the RHP side. So it is unstable. Now we know that the A matrix for both uh, other equilibrium points are same 1 0 and minus 1 0, so we can consider any one of those because the A matrix is same, eigenvalues will be the same, so the stability will also be the same 1 0 transpose and minus 1 0 both have the same A matrix, so the stability also will remain the same. So it is 0 1 2 minus 1. A is 0 1 2 minus 1. Okay, now let us see what happens. So my A is this, so determinant of lambda I minus A. So it is 0 means lambda, minus 1, minus 2, lambda plus 1, right? 0, 1. Wait a minute. I think I have made a mistake. Oh, this is minus 1. 1 and minus 1. I think I have made a mistake. So this should be minus 1. So this is minus 1. Similarly, this will be also minus 1. So it will be minus 1. The other things are fine. So if this is minus 1, say this is minus 1, then this will be lambda plus 1. So it will be lambda square plus lambda. So it is minus 1 plus or minus square root of root 3 by 2. So it is minus zero point 0.5 plus root 3 by 2 and minus zero point 0.5 minus root 3 by 2. So the eigenvalues are on the LHP, one in the Q2, one in the Q3. So we have made a mistake. So it is not unstable, it is rather stable because it is in the LHP side. So let us do it once more, cross check so that we will not make any mistakes. So it is x2 means 0 and 1. So it is 0 and 1. This is minus 1 plus 3x1 square and minus 1. So minus 1 will be there and 0, 1, minus 1 are common. So 0, 1, minus 1 are common. And if this is 0, this will be minus 1. So if this is this lambda 1 become minus 1 will become 1. This will be lambda plus 1. So lambda square plus lambda plus 1. So it is minus zero point 0.5 real part. So it is in the LHP side. So it is stable. Now let us calculate this. Sorry, it is determinant. So if we calculate, we will get lambda square plus lambda, then minus into minus 2 into minus 1. So it is minus 2 equals to 0. So now lambda is minus 1 plus or minus square root of b square minus 4ac. So b square minus 4ac will be 7, or let us check. I think it is factorizable. My bad. So this can be written as lambda plus 2 into lambda minus 1 equals to 0. Yeah. So it is factorizable. We'll get lambda equal to 1 comma minus 2. So in the above case, the real part for both the eigenvalues is negative and both are lying in the LHP. So it is stable. Whereas in this case, one is in the LHP, one is in the RHP. So this is unstable. So we made a mistake earlier and we have rectified it. So this is unstable and the other one is stable. So out of the three equilibrium points, one equilibrium point is stable and the other two equilibrium points are unstable. So in stability as well as instability also, there are multiple categories in the way how x1 and x2, if we draw the plot of x1 and x2, it is called phase portrait. And then in that we can see how x1 and x2 are moving, and then accordingly also we can design, accordingly we can decide uh, what type of stable, if it is stable, what is, there are subcategories like circle, focus, stable focus. Uh, in the case of instability, there is something called saddle point, unstable focus. So there are certain things, but we are not going into the details. It will be covered in a different course, and this course doesn't cover those aspects. So we'll leave it stability and instability. So one is stable and the other two are unstable. So with that, if you have any questions, you can ask, else we'll move to the subsequent discussions. So there are two more topics that are left. One is the canonical form, another one is the exponential matrix. So first we'll start with the canonical form. Previously we have discussed state space to transfer function is unique. Transfer function to state space is non-unique. So let me rewrite it again. State space to transfer function is unique and vice versa is not. So when we say non-unique, so there are multiple possibilities, and now we are going to discuss about three of them. So one is controllable canonical form. The other one is observable canonical form. And the last one is diagonal form. Okay. So we have three such ways of representing the same transfer function. As we said, it is non-unique, and these three are widely used. It's not that it is limited to three. There can be multiple or n number of ways to model the same transfer function in state space representation. However, we'll be discussing about three such in today's discussion. So g of s is given as something like this. So now I can call this as y of s by h of s. Sorry, y of s by u of s. So what I would do is I will cross multiply and then convert it into time domain, like how we have solved that linear differential equation. So first I'll start with the controllable canonical form. Controllable canonical form. Okay. So s cube into y of s. So if we do that, we'll get s cube into y of s plus 6s square y of s, 6s square y of s plus 11s y of s, 6y of s, 11s y of s plus 6y of s is equals to u of s. So this is what we have obtained. Now we can convert it into time domain. So s cube will be y triple dot y triple dot plus 6 into y double dot plus 11 into y dot plus 6 into y equal to u of t. So I think it might rain here. I just hope that the power will not go off and we will be able to continue our session. So this is what exactly we have solved at the beginning of the session, and we have told that first check the order of the system. The order of the system is 3. Order is 3, which means 3 state variables or 3 states. 3 state variables. So this makes our life simpler. We'll follow what exactly we have done at the beginning of the session. So my 3 states, I'll start with y and then I'll take the derivatives. So x1, let me choose a different color. So I have 3 states. So x1 is one state, x1, then x2, then x3. So x1 is y, x2 is y dot, x1 is y double dot. So from this, if you calculate now, x1 dot is nothing but x2, x2 dot is nothing but x3, and x3 dot is y triple dot is what we get from the original equation. So x1 dot is x2, x2 dot is x3, x3 dot is what? Minus 6x1 minus 11x2 minus 6x3 plus u of t, which is what we are getting from the given equation. So this equation, whatever is this equation, if we calculate y triple dot, it is the x3 dot, and from there we are going to get the final equation. So now this final equation, we are going to write this in terms of A matrix, B matrix, as well as C matrix, as well as D matrix, and from there we'll get the A, B, C, D. So that is one set of state space representation, which is called the controllable canonical form. And we have also discussed this at the beginning of the session, today's session. Okay. So now if I write this in terms of matrix, let me write it. So we have x1 dot, x2 dot, x3 dot, and then we have a matrix 3 cross 3 multiplied by x1, x2, x3. So this is 0, 1, 0, 0, 0, 1, minus 6, minus 11, minus 6, plus u is having a column vector. So we have 0, 0, 1 into u, 0, 0, 1. And then y, my output y is nothing but x1. So it is 1, 0, 0. C matrix is 1, 0, 0. So my output y is equals to 1, 0, 0 into the state vector x1, x2, x3 plus d into u. Okay, so in this way we'll get the ABCD matrices. So now this is called controllable canonical form. But for observable, we are not going to do any of these things. So we just will take the transpose of this. So observable like a dual. So controllable and observable canonical form. If we obtain one, we can get the other one, which is they have the duality principle. So we just have to interchange the matrix, and then we'll be getting the observable canonical form from controllable and vice versa. So observable canonical form. So let me open a new page. So controllable is done. Now observable canonical form. Okay, observable canonical form. So uh, it is obtained from this only. So I'll put this on the corner, small, and then we'll update this over here. So this is the controllable canonical form. Okay. So now we just have to do the transpose of the matrix, and then we are there. So rows becomes columns, columns becomes rows. So it is simple. Here also this will be interchanged. Yeah, and then D will remain the same. So the first row 0, 1, 0 will become the column here 0, 1, 0. And then the second row 0, 0, 1 will become second column. And then the third row is minus 6, minus 11, minus 6. And then 0, 0, 1 will become 1, 0, 0. And then 1, 0, 0 will become 0, 0, 1. So in this way, once you get the controllable canonical form, you can get the observable canonical form. So the controllable canonical form is what we have discussed thoroughly. We'll start with one of the state and then take the derivatives of those states as the other states, and then we'll try to get the ABCD matrices. Once we get those, then we have obtained the controllable canonical form. So now interchange the elements in the matrix by applying the transpose or finding the dual of the matrix, and then we are there. We'll get the observable canonical form as well. So these two are related to each other, whereas the third one, it is the diagonal form where you have to apply the partial fraction. So it is slightly different from the other two. Now we will be discussing this. So the diagonal form, observable canonical form is there. Now the diagonal form. Okay. So diagonal form is nothing but y of s by u of s, which is given by, sorry, 1 by s cube 6x square 11s and 6. 1 by s cube 6s square plus 11s plus 6. Say this is a third order, right? Now I'll get c1 by s plus p1 plus c2 by s plus p2 plus c3 by s plus p3. So now I have to uh, differentiate each of these I mean, factorize the denominator and then apply partial fractions to get each of these expressions. Now we'll deal with this individually rather than combining it. We'll deal with this individually. So let us see how we are going to get, because we have already discussed partial fractions multiple times. I'm not going to derive those. Rather, I would uh, choose an alternative where I have code, and then I'll put the inputs and then I'll get the output. So this is the code where we have cleared the workspace as well as the command window. And then the numerator is 1, denominator is s cube plus 6s square plus 11s plus 6. And then this is the command residue of numerator and denominator. Sorry. So this is the command which will have the residue, which is the constant. And then P is the pole individually. And then the direct term means if there is, if it is, say here we have a strictly proper transfer function, where if it is proper, then you will get, you can take common, right? So you will get one constant, maybe one, maybe half, two. So that is the direct term. So now let me run this. So if I run that, I will get residues as 0.5. So C1 is 0.5, P1 is -3, -1 and -2, and zero point 0.5 and -1. So first let me write C1, C2, C3. So residues are C1, C2, C3. So C1, C2 and C3, and the orders are very important. If we mess up the orders, then we'll get a wrong result. So P1, P2 and P3. So starting with the residues. So residues are my constants. Uh, zero point 0.5 -1, 0.5. 0.5 -1, 0.5. And then the poles. -3, -2, -1. -3, -2, -1. Okay. So now let us see how we are going to get the y of s by u of s. So my y of s by u of s is nothing but C1 0 0.5 by, sorry, this is s minus pole, right? P1, P2, P3 are the poles, so it is not my plus, so my bad. S minus, yeah. So it is s plus 3 plus -1 by s plus 2 plus 0.5 by s plus 1. So now what we will do is we'll take the u of s that said and then see how we are going to get. Okay. So y of s is 0.5 into u of s by s plus 3 minus 1 into u of s by s plus 2 plus 0.5 into u of s by s plus 1. Okay. So now let us consider these things as, say this is x1 of s, this is x2 of s, this is x3 of s. So now we'll get y of s is 0.5 into x1 of s minus x2 of s plus 0.5 into x3 of s, as if we have three states, and then it is an algebraic summation of these three. So let us solve one by one, but once we solve one, we'll be able to get the other two as well. So kindly notice what I'm doing. So my x1 of s is u of s by s plus 3. So now if I substitute, I mean cross multiply, I'll get s into x1 of s plus 3 into x1 of s is my u of s. So if I do the inverse Laplace transform, I'll get x1 dot plus 3x1 is equals to u. So my x1 dot is equals to minus 3 into x1 plus u. So I have directly gotten the equation because it is a first order. So my x1 dot is obtained as minus 3 x1 plus u. Similarly, I can do for the other two. So let me move this to the side a little bit. Okay. Now let us solve for x2 of s. x2 of s is u of s by s plus 3. That implies s into x2 of s plus 3 into x2 of s is equals to u of s. Now x2 dot plus 3x2 is equals to u. Sorry, it is s plus 2. This will be 2. So that will be x2 dot is equals to minus 2x2 plus u. Now the third one, x3 of s is equals to u of s by s plus 1. That implies s into x3 of s plus x3 of s is equals to u of s. Apply inverse Laplace transform. x3 dot plus x3 is equals to u of t. So we'll get x3 dot is equals to minus x3 plus u. So this is the last. So we got the states. Now what about the output? But output I can get from here itself. So let us see what I'm going to do now. Okay, so this is there. Okay, so we have y of s, which is 0.5 into x1 of s minus x2 of s plus 0.5 into x3 of s. So if you apply inverse Laplace transform, we'll get y of t is equals to 0.5 into x1 of t minus x2 of t plus 0.5 into x3 of t. So we got all the equations. Only thing we have to rewrite them in terms of matrix. So I will be taking all these three. Okay. So now I'll write x1 dot x1 dot x2 dot x3 dot into x1, x2, x3 plus we have b into u. Now we have y, which is equals to c, which is a row vector into x1, x2, x3 plus d, which is 0 into u. Okay. So x1, x2, x3. So x1 dot is minus 3x1. So minus 3, others are 0, and this is 1. x2 is minus 2x2, 0, minus 2, 0, and then 1. x3 is minus x3, 0, 0, minus 1, and then 1. And then y is 0.5 x1 minus 1 x2 0.5 x3. As you can see, this is the diagonal. You can see it's a diagonal matrix. So that's why it is called diagonal form. So each of them are having a different A matrix, different B matrix, different C matrix. However, all of them will lead to the same transfer function. And here we have considered three such case studies, but it need not be limited to three. There are n number of ways to represent the given transfer function into state space form. So just to quickly summarize what we have discussed, because we have discussed multiple things, I'll just quickly summarize. So in this canonical form discussion, we have been given one transfer function, and then we are asked to get the different types of canonical form representation of the given transfer function. So we have realized the transfer function to state space is non-unique. So starting with the controllable canonical form, we have cross multiplied and then considered y as one of my state, and then considered the other states as the derivative of this y. Once we have obtained that, then we have tried to get the individual equations and then try to represent in terms of a matrix form. And then that will give me controllable canonical form. Now by applying the transpose of each of the matrix and moving the elements in the matrix, I'll get the observable canonical form, which is what we have gotten. And for the diagonal form, we have to factorize this denominator and then apply partial fractions. So we have used the MATLAB code to save our time, but you can always do during your leisure time. And once we get the pole locations as well as the constants, we have obtained the uh, this individual separated transfer functions. Now individually we have solved, and then basically since these are separated, x1 is not dependent on x2 or x3 and vice versa. So all of them are basically decoupled. So in this case, our x1 dot, x2 dot, x3 dot equations we have obtained. Similarly, y is also a function of x1, x2 and x3. So once we write the matrix, we will be getting in this way. So we have represented the same transfer function in three types of way, which are respectively controllable canonical form, observable canonical form, and diagonal form. So if you have any questions, you can ask. Else, I'll move to the final topic of today's discussion, which is the matrix exponential. So any queries till this point? No. Okay. So,
No, sir. Thank you.
sorry.
No, sir. Thank you.
Okay. Okay. Yeah. So matrix exponential is basically e to the power at. How are we going to calculate e to the power at? So first, whatever we have x dot is equals to. There is no noise from my room, right? Because it is raining heavily outside. Is the voice audible or there is noise?
It's okay. No, no noise, I think.
Okay. Okay. Just let me know if there is noise. I'll close the door and window.
Sure.
X dot is ax plus bu and y is cx plus du. So how are we going to calculate e to the power at? So the point is, how are we going to calculate e to the power at? Okay. So first let us see, there is one expansion of Si minus A inverse. Si minus A inverse can be written as an exponential as I by S plus A by S square plus A square by S cube plus up to so on. So this is a standard formula that we have. But how do we know that this is correct? So first let us validate it that it is correct, and then we'll move to the subsequent derivation. Okay, so this is the formula. So now how am I going to check whether this is correct or wrong? So I'll multiply by Si minus A on LHS's RHS side. So if I multiply, I'll get Si minus A into Si minus A inverse is nothing but Si minus A by S plus Si minus A into A by S square plus Si minus A square, Si minus A into A square by S cube plus up to so on. So now this is I minus A by S plus SS will get cancelled, A by S minus A square by S square. Here SS will get cancelled, A square by S square minus A cube by S cube plus up to so on. If you see, all of this will get cancelled. So this will get cancelled with this will get cancelled with this will get cancelled with this. So finally on the LHS side we have I, on the RHS side we have I. So it is true. So now using this Si minus A inverse, how am I going to calculate e to the power 80? So first let us rewrite this Si minus A inverse again. Si minus A inverse is equals to I by S plus A by S square plus A square by S cube plus up to so on. So now let us do Laplace inverse of this. So Laplace inverse of Si minus A inverse. So left side is Laplace inverse of Si minus A inverse. Right hand side, I by S is nothing but I, right? Because S is U of t, so we have I. And 1 by S square is what? T, right? So it is AT. And S cube is T square by 2 factorial. Plus, if you calculate A cube, T cube by 3 factorial plus up to so on. So now this is nothing but e to the power 80. So in this way, we can calculate e to the power 80. So if you calculate Laplace inverse of SA minus A inverse. So if you see on one side, we are calculating everything in S domain and then applying inverse Laplace transform to get e to the power 80. So this is one way to do. So now the formula is basically e to the power 80 is equals to Laplace inverse of SA minus A inverse. Yeah, so e to the power 80 is nothing but Laplace inverse of SA minus A inverse. So in this way, we'll get the e to the power 80 expression for a given A matrix. So if A matrix is given, how can we calculate e to the power 80? First, we have to calculate SA minus A, then SA minus A inverse, then Laplace inverse of that. So this is a simple concept, but let us apply and solve a few problems and then see how we are going to get. So here I have given one such example, two such examples, to be honest. And first A matrix is diagonal, second A matrix is non-diagonal. So the first one is going to be easy because it is diagonal, inverse will be easier to find. The second one, it will be a little bit critical, but let us see. So the first one, A matrix is -1, 0, 0, -2. So first I have to calculate SA minus A. SA minus A is S plus 1, 0, 0, S plus 2. Okay. Now from this, I can also calculate mod SA minus A. Mod SA minus A is S plus 1 into S plus 2. Okay. Now, how can I calculate SA minus A inverse? It is adjoint of SA minus A by mod of SA minus A. So this will be S plus 2, 0, 0, S plus 1 matrix into 1 by S plus 1, S plus 2. Okay. So now I have to apply Laplace inverse. So Laplace inverse of SA minus A inverse is equals to 1 by S plus 1, 0, 0, 1 by S plus 2. Okay. So it is Laplace inverse of SA minus A inverse. Now, sorry, I think I should not have written like this. So this is SA minus A inverse. So this is SA minus A inverse. Now I have to calculate Laplace inverse of SA minus A inverse. It will be e to the power minus t, 0, 0, e to the power minus 2t. So in this way, we can calculate Laplace inverse of SA minus A inverse. So now this is nothing but e to the power at. So for a given A matrix, we have obtained e to the power at is e to the power minus t, 0, 0, e to the power minus 2t. So this is how we get. So just to cross check, we can put t equals to 0 and then see whether it is identity matrix or not. So what we can do is we can put t equals to 0 to cross check. So put t equals to 0. Then you have on the LHS side e to the power 0 is basically I. On the RHS side e to the power 0 means 1, 0, 0, 1. So this is just to cross check whether what we have done is correct or wrong. So we have cross-checked that it is coming to be correct. So for the first matrix, we have seen that it is little bit straightforward, and then we have gotten the exponential matrix or the matrix exponential. Now we'll do the same and then follow the same and then calculate for the other one. 0, 1, -2, -3. So the second one, A is 0, 1, -2, -3. So let us do the same. First, we'll calculate SA minus A. So we'll get S minus 1, 2, S plus 3. So this is SA minus A. Now let us calculate the determinant of SA minus A. It is S square plus 3S plus 2, which I can write it as S plus 2 into S plus 1. Okay, now I have to calculate SA minus A inverse, which is 1 by determinant of SA minus A into adjoint of, so adjoint of SA minus A. So it will be 1 by S plus 1, S plus 2 multiplied by S plus 3, 1, minus 2, and then S. Right? Yes. So now let me take it to the next page. So if I calculate, now my SA minus A inverse is nothing but S plus 3 by S plus 1 into S plus 2, 1 by S plus 1 into S plus 2, minus 2 by S plus 1 into S plus 2. Then last one is S by S plus 1 into S plus 2. Okay. So this is the matrix that I have obtained. Now I have to apply inverse Laplace for each of these, for which I have to again perform the same thing, which is partial fractions, which I want to skip, and then I'll be using MATLAB just to save time. But you can always uh, do during your leisure time and then have much more practice. But for the time being, let us just use the MATLAB. So my numerator is what in the first case? S plus 3, S plus 3. And then denominator is what we have calculated, S square plus 3S plus 2, S square plus 3S plus 2. So let me do that. If I run it, I'll get constants to be -1. So for -1, it is, so we have to be very careful. We should not make any mistake. So first, let me write the first expression. First expression is -1 by S plus 2. So we'll get -1 by S plus 2 plus minus 2, 2 by S plus 1, 2 by S plus 1. So we can actually combine and then check. So it will be minus S minus 1 plus 2S plus 4. So it is S plus 3. So it is coming to be correct. So now the second one will be 1 by S plus 1, S plus 2. So I will consider this 1 by S plus 1, S plus 2. So it is -1 and 1. So -1 by S plus 2 and then 1 by S plus 1. If you multiply, you will get minus S minus 1 plus S plus 2. It will be 1 by S plus 1 into S plus 2. So for the last one, I have to multiply by -2. So it is simple. We'll have 2 by S plus 2 and then minus 2 by S plus 1. So if you multiply, it will be 2S plus 2 minus 2S minus 4. It is -2. And then the last one is S by S plus 1, S plus 2. So it is S plus 0 by S square plus 3S plus 2. So we have 2 and -1. So it is 2 and -1. So it is 2 by S plus 2 minus 1 by S plus 1. So this is the overall matrix that we have obtained. If I cross check the last one, it is 2S plus 2 minus S minus 2. So it is basically S in the numerator. So it is simple. partial derivatives, I have just used MATLAB so that we can save time and then discuss the subsequent part in detail, not to skip it. Now we can apply the inverse Laplace transform. So if you apply the inverse Laplace transform, then we'll get minus into e to the power minus 2t plus 2 into e to the power minus t. Here we'll get minus into minus 2t plus e to the power minus t. Here it is 2 into e to the power minus 2t minus 2 into e to the power minus t. The last one is 2 into e to the power minus 2t minus e to the power minus t. Okay, so I have obtained in this way. So this is the inverse Laplace transform of Si minus A inverse, which is our e to the power at. So let us write it again. E to the power at is equals to minus e to the power minus 2t plus e 2 into e to the power minus t, e to the power minus 2t plus e to the power minus t, 2 into e to the power minus 2t minus 2 into e to the power minus t, 2 into e to the power minus 2t minus e to the power minus t. So this is what we'll be getting. The matrix exponential, and always cross check. So t equals to 0, put t equals to 0. On the LHS side, we have I, e to the power 0 is I. Here we have minus 1 plus 2, 1. This is minus 1 plus 1, 0. 2 minus 2, 0. 2 minus 1, 1. So our whatever we have obtained is correct. So it is correct. So it is correct. So in this way, we can actually solve for the matrix exponential and then see. So if you see, the second part is a little bit complicated because it is not diagonal. So finding the inverse and then inverse Laplace transform will be a little bit difficult. Whereas in the first case, it is going to be a little bit easy. So in this way, we can calculate the matrix exponential. If you have any doubts, you can ask me, else I'll just summarize this session and we can end today's session. Any doubts until this point?
No, sir. Thank you.
Okay, okay. So I'll quickly summarize today's session. Yeah, so today's session is about state space analysis. So first we have started with why transfer function based design has a few drawbacks. So first, what are the advantages? It has been widely used in the industry and it is also easy to use because of the algebraic property, and it is also very dominant approach. However, it is only limited to the linear systems and also limited to single input, single output systems. So we need more generic model which is applicable for nonlinear systems as well as multi-input, multi-output systems. So that is using state space. So we have started with the state space model. We have defined a generic nth order model, and what will be the A matrix, B matrix, C matrix, D matrix for an nth order. We have written a generic form, and after that we have solved one problem quickly where we were asked to obtain the state space equation from the linear differential equation. So in this case, we have been given one third order linear differential equation. So we have considered y to be our state and the subsequent states to be the derivative of y, and how many such states we have to consider, same as the order of the system. Since it is third order, we have to consider three states. Then we have calculated the derivative of the states and obtained the equations, and then we have written in terms of a matrix form. So in that way, we got the ABCD matrix. Then we have learned how to get the transfer function from the state space. Again, this is unique, whereas the vice versa is non-unique. So we have to apply the in Laplace transform and then solve for x of s and then substitute it in the second equation. In such case, we'll get the transfer function to be c into Sa minus A inverse into B plus D. So once we have solved that, we are going to convert our state space to the transfer function. So we have been given A, B, C, D matrices. We have to calculate C into Sa minus A inverse into B plus D. So individually we have solved, and then finally we got the transfer function. And now we can comment on the stability of the system by calculating the poles of this. Or you can also calculate the eigenvalues of this. Both will result in the same thing, unless there are some pole zero cancellation. So eigenvalues of A will be like the best way to get the overall uh, eigenvalue locations, whereas during the calculation of transfer function, there can be some pole zero cancellation. So g of s will be same as the order of the A matrix, or it will be lesser than that. So it is always better to calculate the eigenvalues of A matrix to comment on the stability. Then we have discussed about the linearization. Why it is important? Because till now we have discussed the linear model, but what if x1 dot x2 dot are a function of x1 and x2, and this function is not linear, say non-linear? Then and again, why it is important? Because majority of the systems in our day-to-day life all are non-linear, so we have to linearize around the equilibrium point. What is equilibrium point? The point at which the state variables are derivative of state variables are zero, which means the state variables are constant. So first we have to calculate the equilibrium point, and at around each of this equilibrium point we have to calculate the Jacobian matrix and also obtain the stability or check the stability at each of this Jacobian matrix. So Jacobian matrix is obtained by partial derivatives of f1 f2 f2 up to so on fn. Similarly, see here it is a single input system, so we'll have one column. If it is multi input, we have multiple columns. Similarly, we'll get the y also in terms of c into xn plus d into u. So first we are calculating the equilibrium points, getting the Jacobian matrix, then calculating the matrix for each of the equilibrium point, finding the eigenvalues of those individual matrices, and then commenting on the stability. So we have calculated one such linearization where yes. So Sarvan Kumar has asked, not linear and non-linear are same. Yes, yes, yeah. So anything that is not linear is non-linear. Like I am using it interchangeably, but both are same. So anything that is not linear is non-linear. Yeah, both are same. That's why I'm using them interchangeably. Yeah, so here we have been given another question where it is non-linear system. So first we have obtained the equilibrium points, and there are three such equilibrium points. Then we have calculated the Jacobian matrix, and we have seen it's a function of x1. Then we have calculated this Jacobian matrix for each of these equilibrium point. So we got the linearized state space model around that equilibrium point. So the state space model will vary around the equilibrium point. So first we have to choose which equilibrium point we are wanting to operate at around, and then we have to use that model. So we have also calculated the stability. We found that around one equilibrium point it is stable, around the other two equilibrium points it is unstable. Finally, moving to the canonical forms, where we are converting the transfer function to state space, which is non-unique. So we have considered three such possibilities which are famous, like controllable canonical form, observable canonical form, and diagonal form. Controllable canonical form is simple. First you convert it into differential equation and consider one y as the state variable and the derivative of the y to be the other states. And how many such we have to consider? We have to consider three state variables because the order is three. Once we get that, write in terms of matrix form, and then you will get the controllable canonical form. For observable canonical form, we have to do the transpose of the matrix, and then you'll get the observable canonical form. So if anyone asks observable canonical form, first calculate the controllable canonical form, and from there you can get the observable canonical form. Whereas in the case of diagonal form, you have to do partial derivatives. So first you factorize the denominator and then calculate the partial derivatives. Once you get the partial derivatives, then individually solve, and then you will get three such independent equations, and then y of t will be summation of this with the proper scalar. So now we have four such equations, and then we have written in terms of the matrix, and we have obtained the final diagonal form, canonical form in terms of state space model. Then we have finally discussed about the matrix exponential, where e to the power at can be defined as Laplace inverse of sa minus a inverse. I have considered one such matrix. One is diagonal, which is simple, and the other one is non-diagonal, which is a little bit complicated. And I have chosen second order. Had it been third order, it will be more complicated, and it will be more mathematically complicated. So just to understand, or just to make you understand the concept, I have considered a simple problem with reduced order, but you can extend the same idea and solve for higher order as well. So this is the first problem where it is diagonal. So e to the power at is also diagonal because summation of n diagonal matrices is a diagonal matrix. And then in the second case, we have also done that SA minus A inverse we have calculated, applied partial fractions, and then applied inverse Laplace transform. And then we got Laplace inverse of SA minus A inverse. So this is the final e to the power at. Always cross check by substituting t equals to 0. It should result in an identity matrix. So in this way, we can solve for exponential matrix as well. And that summarizes today's discussion. Any queries until this point? If you have any queries, you can ask, else we can end this session here.
No, sir, thank you. Thank you very much.
Okay. Yeah, thank you for joining and staying towards the end and the entire session. Yeah, with that, we'll wind this session, week 11. And yeah, all the best for your week 11 assignments. I hope you are going through the YouTube videos. And we'll again meet on next Monday with week 12 content. And again, there will be one problem solving session, one hour session, final session on Tuesday. And you'll be informed by the NPTEL support team via mail. So with that, I wish you all the best for your week 11. And I'll
It's
end
next
the.
week or
Yes, yes.
next
So next week,
another
Monday, we'll have
session?
week 12 session, 2 hours. And Tuesday, we'll have 1 hour session, which will be like the final doubt clearing session before the your final exam. You'll be informed via
So
mail as well.
it is covering all the tutorial, right? Previous
Yes, yes. So
all
I'll
the
just
module.
quickly go through my
module.
notes and then like just summarize it. If you have any doubts, you can ask. It is more of summary. If you like have questions, you can ask. Else, I'll be showing my notes from starting to ending and then just
Okay.
brushing up everything what we have discussed in all the
Okay.
weeks.
Okay. Sure. Thank you.
Okay, okay. Okay, then I wish you all the best and I'll end this session here. And yeah, good night and please solve all the problems by going through this.
Okay. Sure.
Okay.
Bye.
Yeah. Good night then.